Kolchmeyer from MIT that will tell us about chaos and the emergence of the cosmological parameter.
Great. Yeah, so thanks very much, and thanks for the invitation to speak here. I'm very happy to tell you today about my work with Hong Lu called Chaos and Emergence of the Cosmological Horizon. So as you know, in recent years, we've learned a lot about the holographic dictionary and ADS-CFT. This includes, for example, the matching of correlation functions on the bulk and boundary side via the extrapolate dictionary, the matching of entanglement entropies on both sides using the Ryo-Takanagi formula, and then more recently, we understand how to use the bulk to probe aspects of chaos and complexity in the boundary dual. So given that we've had so much success in understanding ADS-CFT and anti-de Sitter holography, it leaves one to wonder whether any of the lessons that we've learned in that context can be ported over into de Sitter space. In particular, in ADS-CFT, even from a purely bottom-up perspective, we have good evidence that quantum gravity in ADS is in fact dual to a CFT. So the question is, what are the kinds of bottom-up calculations or approaches we can take in de Sitter space to give us more confidence that there's a holographic dual, and if so, what are the properties of this dual? So perhaps, taking a page of the ADS, it would be nice if we had a timeline holographic screen somewhere in the book. And so there seem to be two different options. One of them is to have a timeline boundary like we would have in ADS-CFT, or to have an observer. And we're going to consider the conjecture that the holographic screen lives on an observer's world line. So this conjecture, I guess, is more than a decade old now. I believe, at least to my knowledge, it first appeared in this paper by these authors over a year ago. And the basic idea is that you can consider correlation functions that live on, or correlation functions of operators on an observer's world line, and perhaps these correlation functions can be reproduced by correlation functions of some appropriate operators in some dual quantum mechanics which lives on that observer's world line. So I think this conjecture has become a lot more interesting after a very interesting paper that came out a couple of years ago by the authors Chandrasekaran, Longo, Pennington, and Whitten. And so they also considered the algebra of observables, or operators that live on some observer's world line. They showed that associated to this algebra is a natural notion of entropy, and this entropy agrees with the generalized entropy of the observer's cosmological horizon. And so I think one interpretation of this is that this gives an additional target or additional task or additional criteria that the putative holographic dual has to obey, which is that we're searching for some candidate holographic dual that can not only reproduce correlation functions along the observer's world line, but also give some statistical interpretation of this entropy, the entropy that was described in this work by CLPW. So because what they did is so important for what I'm about to say, I'm just going to give a very broad review of what they did. So CLPW considered global de Sitter space with two observers at the north and south poles. So that's what I've depicted here in the Penrose diagram for this. So AR refers to the algebra of operators that belongs to the static patch of the right observer, and it's also all those operators are gravitationally addressed to the world line of the right observer, and A left is defined analogously. And so one result they showed is that these algebras factorize. And so by that I mean that the commutant of AL is equal to AR and vice versa, and also the intersection of these two algebras is trivial, just multiples of the identity. And the key point is that these algebras factorize even though the Hilbert space does not factorize. So even though you don't have Hilbert space factorization, there's still a sense in which the entire space-time can be partitioned into two different subsystems. Furthermore, although we don't have separate Hilbert space factors, one can still define a trace on the algebras AL and AR. So in particular, for some reduced density matrix rho in AR, one can compute minus trace rho log rho, and that's the entropy that has been shown to agree with the generalized entropy associated with the observer's cosmological horizon. So, of course, there's a similar story in ADS-CFT. This is just describing semi-classical gravity. So in ADS-CFT, this would be a two-sided black hole, and AR and AL represent the algebras that live on the exterior regions of the black hole. And in this case, there's a microscopic explanation for this algebraic factorization, and that's because underlying this two-sided black hole, there's actually, at finite n, there's a factorized Hilbert space that corresponds to two different CFTs. So one of the messages of this talk is that when we move away from some parametric limits, this de Sitter algebraic factorization actually fails due to chaotic observer dynamics. And so by that, I mean the following. So we can consider, the observer sitting at the North Pole, and now imagine that at some point along their world line, there's some small fluctuation of the metric, or maybe they interacted with some particle that imparted some momentum to this observer. So this will cause the trajectory of the observer to deflect, and it will become some other geodesic now. And then due to the exponential expansion of de Sitter space, the deflected trajectory of the observer will eventually come into causal contact with the other observer. So that means that the algebras can't factorize anymore because you can't have commuting operators in all states. In other words, there are states in which one observer can send messages to the other. So the algebraic factorization fails. Yeah.
Sorry, we talked about this a little bit yesterday, but maybe from a different angle that would raise my skepticism. I mean, holography is about, it's something that happens only when gravity is turned on.
Yes.
It's about being able to reconstruct from boundary data, let's say near the boundary of ADS, deeper into the bulk. It's something that cannot and should not happen when gravity is turned off. Now, when gravity is turned off, you can discuss these algebras of QFTs on a fixed background.
Yes.
When gravity is turned on, the holographic principle is precisely the statement that those degrees of freedom and those operators aren't there and don't make sense.
Mm-hmm.
So, I feel like, okay, in AES, asymptotic AES, we have a holographic theory. We can ask if there's some crazy limit we can take where the holography goes away and we recover quantum field theory in a fixed background.
Mm-hmm.
And that's an interesting question, and it's been studied, and we know what crazy limit to take.
Mm-hmm.
And so we can go out of our way to recover not holography,
Yes.
right?
Mm-hmm.
In de Sitter, we have absolutely no idea what the right theory is.
That's right.
And it seems to be like we're just moving around our not holography. I don't understand what we're doing here that's not just trying to rephrase how we already know quantum field theory and fixed background works when there isn't any gravity, in the language of, in this case, a theory we don't know.
Right. That's right, yes. So we don't know the theory, so all we can do is conjecture. Well, first we can conjecture that the theory exists and then try to explore the consequences of that. So basically this talk is predicated on what hopefully is a very minimal conjecture that you could try to associate some dual description along an observer's world line. So for example, I'm not the first person to make this conjecture. There was a paper from Whitten called The Background Independent Algebra in Quantum Gravity where I think he was saying the same thing, that there's some algebra.
Yeah, that doesn't mean that it makes sense.
No, sorry.
Sorry.
No, that's a fair point. No, sorry. I didn't mean to imply that. I'm just saying.
I mean, in the case of, how did we discover the CFT group ADS? We didn't discover it by studying, algebraic quantum field theory in causal diamonds. We studied it by looking at the structure of the asymptotic symmetry.
Yes.
The reason that makes sense is that the asymptotic region is something you can sort of fix, right?
Yes.
Here you have nothing you can fix.
That's right. We don't have this asymptotic
So there's,
region.
this world that we're putting there, or this world line, it's not a thing. It's not something that gravity is going to respect. It's not something that. It's not an anchor on which you can anchor some theory. That's why I'm troubled.
That's true. Well, I think part of the motivation is that by taking this approach, it was possible to give some different interpretation of the generalized entropy of this horizon of the static patch. And I think that's a very, like when people want to explore holography in this other context, part of it is trying to understand where this entropy comes from, or why this horizon seems to obey like horizon thermodynamics. So people are looking for some microscopic understanding of that. And so here they show that this generalized entropy is associated with an observer's world line. And so I'm just taking that as motivation to explore the idea further. Suppose we can define operators that are localized on the observer's world line and compute their correlation functions. Maybe there exists some theory, some dual description that also knows about these correlators. And we would use this as a starting point to discuss the emergence of the algebras of this observer. But this is just a conjecture, and I don't know, we have to start somewhere, I guess. Yeah, so really the point of this talk is let's just conjecture that this idea of a holographic screen along the observer's world line is correct. It seems appealing from one angle because one can make a connection between that and the entropy of the horizon using this type 2 entropy, but I just want to push this idea further. And we'll see what happens. Yeah. Thank you. Okay, good. Yeah, so the first thing that we're going to see is that the algebraic factorization fails. So I think one conservative conclusion from that is that even if we assume that one observer has a holographic screen, the presence of two observers shouldn't imply that there are two holographic screens. In other words, this naive picture of like a thermal field double state that describes these two patches doesn't seem to hold up, I think. Okay, so now let me just summarize the main results of this work. So one of the technical results is a prescription for addressing local operators to an observer, even in the case where the observer's Compton wavelength is cosmic scale. So in other words, we're going to consider the case where the observer is described not by a geodesic, but by a wave function that can spread out, and so some new idea is needed if we want to talk about address local operators in this more quantum regime. Another result is that, or it's an argument that the commutants of the algebra of local operators, that is addressed to one observer, is generated by the Hamiltonian of the other observer. So in other words, in contrast to what we saw in this CLPW story, the commutant of one of the observer's algebras is almost trivial, and then this can be used to show that their algebra is a direct integral of type 1 factors. So there's some more general algebra that's not even a factor, and then the claim is that when we compute correlation functions of operators, of appropriate operators in this algebra, and take an appropriate semi-classical limit where the observers have very large mass, and the geodesic approximation is valid for describing their dynamics, that these correlation functions would reproduce those in the type 2 algebra. So there's a sense in which this type 2 algebra is an emergent algebra from this other description. Next, we also give a definition for the Hartle-Hawking state. So the reason why this is important is because in this work of CLPW, one of the ways you could define the Hartle-Hawking state would be the state whose expectation value furnishes the unique trace on the algebra that they introduced. And their algebra was a type 2 factor. So in our case, we don't have this type 2 factor structure anymore, so we can't say that we're looking for a state whose expectation value gives us the unique trace, because there is no unique trace. So we have a different definition for the Hartle-Hawking state, which I will present. And then lastly, we can compute in the Hartle-Hawking state an out-of-time ordered correlator of operators on the observer's world line. And we can compute this in a regime where we see this chaotic dynamics I mentioned in the previous slide. So there's a scramble in time that's logarithmic in the observer's mass. And also we can compute the Lyapunov exponent, which is 4 pi over beta de Sitter, which also raises questions about what this putative dual theory is like. Okay, so this would be a good time to break for questions before I go into the more technical setup.
Has anybody tried to do this in ADS, where it would maybe there would be an opportunity to connect to the setting where you understand better, like what happens if you put a world line in ADS and just
Well, yeah, I mean, people have considered observers in ADS. I don't know if people have considered. Yeah, good. So what you're asking is that. Well, yeah, I mean, well, there was recent work. For example, I guess Luca had some recent work considering observers in like closed ADS universes, and then.
no, just I'm trying to put it into like the most boring setting possible, like the one where we understand a lot of the events.
Okay.
So
Is it not possible to use ADS safety and time electric field?
well, I mean, one point I'd like to make is that if you have a generic state in ADS and you put, you evolve it, it's going to evolve into a black hole.
Mm-hmm.
And so this observer's world line isn't going to last for very long.
Yes.
I think in de Sitter, there are reasons why black holes will be thermally produced. So again, I think the idealization of an infinitely on the world line.
So you mean their world line will cross the black hole horizon?
Yeah, and then we terminate it after a finite time.
That's not so trivial. It's not boring, trivial. So.
No, it's not a trivial set, but my point is that the question is like, is there any setup where we have more control than in de Sitter, where we can get some mileage out of this idealization of an infinitely on world line that somehow replaces the usual way we think of logography and becomes a holographic suite. Because if this is supposed to work in de Sitter space, it better work in any other space. I mean, there's nothing. De Sitter is about the hardest you can get. So there should be some version of this in settings that we have more control over.
I think it is most trivial limit is good that geological as it to infinity, then it
Yes.
safety and
Yes.
electric theorem. The question is being an off. Right?
Yes, that's
and
right.
that alternative regime might be, inside the black hole is probably as difficult as.
Can you refer to boosted geodetic that starts near minus infinity at the boundary and ends at near plus infinity at the boundary?
Might be something like that.
Yeah, so
Sorry,
interesting.
boosted curve.
Yeah.
Geodesics responded.
You mean a constant? Yeah, you mean
Yeah,
a constant acceleration kind of thing? Yeah.
Yeah.
Yeah, that would seem nicer. Yeah, I get
Yeah.
Maybe a more technical question. In a type 1 algebra, there's a good definition of pure states.
Yeah.
What does that pure state represent?
Well, you should just think of pure states as being just pure states in the Hilbert space of the entire universe. This is sort of the reason why this algebra is type 1 is morally just because the algebra associated to the entire universe is type 1.
I see, and secretly the algebra that the observer sees is the entire algebra.
Yeah, the observer
it's not just
has-
AL times 0.
Yeah, the observer has access to the entire universe essentially.
Yeah.
Okay. Okay, I guess I'll move on now. Okay, so so let me just make a couple. So I'm just going to describe now our setup of our quantum observer. So this is the action, the world line action for a particle. And so basically our action for the observer is just going to be to promote this action for the particle by introducing, or by basically taking the mass of the particle to be some dynamical field along the observer's world line. So in other words, we should think of the observer as a clock, some clock that's modeled as a point particle. The clock can have different energy states, and then the energy state that the clock is in is the rest mass of the particle that describes the motion of the clock. Okay, so the action for the observer looks just like the action for the particle, except the mass m is promoted to q, which becomes a dynamical field, and has a canonical conjugate field p. Okay. So when it comes to quantizing these things, the first step is to quantize the action for a particle in the Sitter space. And I'll discuss that more on the next slide, but basically once we quantize the action S particle, we're going to get a Hilbert space called H particle, and the orthonormal basis of this Hilbert space, let me just call it n for now, where n is an integer, and it's normalized canonically. So once we've solved that problem of quantizing a particle, to quantize the observer, all we have to do is introduce an extra quantum number to our orthonormal basis, which is the mass of the observer. And so I'm going to work in a convention where it's more, okay, so for me it's going to be more convenient to use a label S that labels the mass. So wherever you see S, just think of that as being the mass. And we're going to take S to be a continuous quantum parameter. And so I'm going to just define an orthonormal basis for the observer's Hilbert space to be normalized like this. So we just label states with the mass and the label n, and then this is their overlap. Okay, and so we're going to be working in 2 dimensions, de Sitter 2, just for convenience. So this slide is really just a review of how we quantize a particle of de Sitter 2. Basically, we have to pick a particular set of positive frequency solutions to the Klein-Gordon equation, which will span the Hilbert space. So here, n refers to the quantized angular momentum of the particle around the cylinder, which is de Sitter 2. Morally speaking, you can think of this mode function psi n as being the analog of e to the in theta minus I omega t, where omega is related to n by the mass shell condition. Okay, so this is the Klein-Gordon inner product for the mode functions. And of course, once we quantize the particle, we're also free to second quantize it to get a scalar field theory. So these mode functions just appear in the decomposition of our scalar field. And then these A dagger operators obey the oscillator commutation relations, and the Hilbert space of the scalar field is given by Fock space on top of a vacuum state, which I'll call the Bunch-Davies state or Bunch-Davies vacuum.
Sorry, this sounds like second quantizing just the word line action, but you also have the P and Q.
Good. Sorry, this slide is just a review of how we quantize a particle to get H particle and how we quantize a scalar field de Sitter. So this slide, I'll talk about the observer next. This slide was just before talking about the observer. Okay, so now we want to quantize the observer. So I'm just going to show you how this picture gets modified slightly. So I have my mode functions, which I call psi. I'm going to, just for convenience, I'm going to trivially renormalize them to get capital psi. And so instead of using the Klein-Gordon inner product on these mode functions, I'm going to use a different inner product here. Okay, so for the Klein-Gordon inner product, we only integrate along a Cauchy slice. But for this inner product here, this actually involves an integration over the entire space-time. So this is perhaps the natural inner product you would write down for, L2 of ds2. And the point is that the overlaps of these mode functions are precisely, give us precisely, the claimed normalization of the orthonormal basis states for each observer that I mentioned on an earlier slide. So the conclusion is the Hilbert space of an observer, H obs, is defined to be the span of these mode functions, where n again labels momentum along the circle, and S is the mass. And then there's an inner product of these mode functions given by integration over the entire space-time. So that's my observer Hilbert space.
Question?
Yeah.
I remember you guys had some comments about how there's some complication with thinking of these wave functions as like overlaps between ascendant states and T theta states. Could you comment on that?
Sure. Well, roughly the idea is that or how should I say this? You maybe well, I guess there's a subtlety, which is that the naive operator that would measure t and theta, like the space-time position operator, actually isn't a good operator because it's not the case. Basically, because those operators don't commute with the gauge constraints that are associated to the different variants of the observer's world line. Yeah, so there's a subtlety there. So in a sense, T and beta are not really good quantum numbers, that they don't correspond to like a gauge invariant operator. The quantum numbers S and N are good though. And so this T and beta just gives a nice way to, well, this is just how we choose to represent this Hilbert space. And it will play a role in our definition of dress operators.
S here, the term is the principal, labels the principal
Yes.
representation of SL2R?
Yes, S labels the principal representation. That's right. Okay. Good. So I told you how we construct the Hilbert space of the observer. So the setup we're going to consider is 2 copies of our observer Hilbert space linked by L and R, and then we're also going to consider HEP-QIS, which is the Hilbert space of a scalar QFT. And so the point is, we can consider these 3 systems, but since we have in mind that this, we're interested in gravity, we have to take into account the non-trivial gravitational constraints. So in gravity, diffeomorphisms are meant to be gauged, and SO2, represents the group of diffeomorphisms that preserve the classical background, which means that the symmetry generators of SO2, have to annihilate all of the states that we actually want to incorporate into our Hilbert space. So the final Hilbert space is going to be this tensor product, but we only want SO2, invariant states.
SO2, is the isometry group once you ignore back reaction on the space-time.
Yeah, it's just the isometry group of DS2.
But if we were to include back reaction, would we still have the quotient? Or?
Yeah, I mean, yeah, even if we include back reaction, there would still be gravitational constraints, but they would look more complicated. We'd have to solve the Wheeler-DeWitt equation. This is essentially, yeah, modeling out by this group is equivalent to solving the gravitational constraints when we have a fixed background. Yeah. Now, I think what you said is very interesting, though, and something I'm thinking about for future work, like having a dynamical metric instead of a fixed background. But for today, the background is fixed. And so the only effect of gravity is to impose these constraints. Good, so we're just looking at the subspace of singlets of the isometry group. And there's a subtlety, which is that basically because SO2, is non-compact, all the singlets have infinite norm with respect to the inner product defined on these Hilbert spaces. So this is a subtlety I'm not going to have time to explain today, but the upshot is that this infinite norm can be thought of as being proportional to the volume of SO2, and so we can formally renormalize all of our states by the infinite volume of SO2, so we do have a procedure for getting a finite inner product from these singlets. Okay, and so the vacuum sector refers to the subspace of H in which the QFT is just in the vacuum sector, which is annihilated by all the creation operators. Okay, so let me just review the construction of states in the vacuum sector. So basically, this means that we have to construct a singlet out of the 2 observer Hilbert spaces, and one condition is that both observers have to have the same mass, and once you fix this mass, then there's a unique state in the Hilbert space. So here, this ket S refers to a state where both observers have a mass given by S, and so this is going to be built out of this this entangled state here in the 2 observer Hilbert spaces. And I can also write this in terms of the mode functions which represent these states. And just for convenience, I'm going to define this expression in terms of the 2 positions to be psi s LR. And so when one computes the normalization of these states and does this renormalization that I discussed, this is the result. Okay, so the physical interpretation of these singlets is the following. So if you have, let's just suppose that you treat the 2 observers classically, then they're described by geodesics, and each geodesic is charged under the generators of SO2, So we have to find some configuration of two geodesics such that the total charges sum to 0, and there's only one way to do that, where one geodesic is sitting at the North Pole and one geodesic is sitting at the South Pole. So this quantum state here is basically a quantum analog of a state where the observers are sitting at antipodes. Okay, so that's how you should interpret this. So it's going to help later. Okay, so very soon I'm going to introduce a diagrammatic language for computing correlation functions. And this state here, ket S, is going to be represented by this picture over here, which is supposed to represent the entanglement between the two copies of each observer. So in the diagrams that I show later, wherever you see this picture, you should replace it in your mind by that function psi LR. In particular, each dot over here represents a point in space-time. So if we look on the right-hand side, the diagrammatic way of representing the overlap between these two states is where I just draw this picture twice. So you have psi LR conjugate, and then the rule is that whenever you have a black dot that has multiple lines coming out of it, we have to integrate over, we have to take that point in space-time and integrate it over all of space-time. That just follows from the inner product we're using on our mode functions. Okay, so this gives a means of, anyway, so this is just a diagrammatic representation for computing the overlap of these two states. Any questions on this so far?
So your definition of the vacuum is there an independent definition than just writing that?
Well, the definition of the vacuum in the QFT is the state that is annihilated by all the annihilation operators, like in the Fock space, or you can also think of it as the unique state that is normalizable and invariant under all the symmetry generators in the QFT.
So you're doing that so the QFT, the free QFT, you're doing that too, but you're also treating the observer psi and L as exactly the same. There's some annihilation operators, I guess.
No. So for the observers are in a first quantized description. So there's no creation of annihilation operators for the observer. Each observer is just a state in the Hilbert space of one particle. But you can think of an observer as the one particle subspace of the QFT.
Okay.
Yeah, and so we're just taking two copies of that observer and then asking for a state that is invariant under the isometries, and you have a one parameter family of such states labeled by the mass, the common mass of the two observers.
Sorry. I thought N was supposed to be the mass.
S is the mass.
Oh, S is the
N is the momentum along the circle. So if N is positive, we say it's like right moving. If N is negative, it's left.
Okay.
Okay, good, thank you. Another quantity that I'm going to use in the diagrams I'm going to show you shortly is something called the observer's propagator. This is equivalent to the Weigand function in a scalar field theory. So in other words, the amplitude for a particle at space-time t1 theta 1 to propagate to t2 theta 2, and it's built out of the mode functions in this way. And just as an exercise, we can multiply this propagator with this state, and there's one point here that's common to the propagator and the state, so we integrate that point over all of space-time, and when we work this out in terms of the mode functions, we have a delta function. And so physically, kind of what's going on here is that there is some operator in my Hilbert space that projects onto states in which the right observer has a given mass. So this PS2, R is a projection operator that just projects into states where the right operator has mass given by S2. And so of course there has to be a delta function that sets S2 equal to S1. And the right observer's Hamiltonian is just defined to be their mass. So I can integrate this projection operator with the expression of the observer's mass. So by now I've introduced states in the vacuum sector of the Hilbert space where we think of the observers as living at the north and south poles, and also there's this Hamiltonian operator that just measures the mass of the observer. So things get a little more complicated when we want to talk about operators that are addressed to the observer's world line. So I want to interpret phi r as a local QFT operator that is essentially evaluated at and addressed to the world line of the bright observer. And so I'll give you the technical definition of that soon, but let me first just show you what its effect is in correlation functions. So when you start with the state where both observers are at the north and south pole, and then act with phi r. So what this does is, it basically creates a particle in the scalar field theory at the observer's world line, and then that particle will get absorbed at another point on the observer's world line here. So this arrow here represents basically the Weidman function, or the amplitude for the particle in the scalar field theory to propagate between the 2 points. Meanwhile, when I act with this dressed operator on the observer's world line, it could change the state that their clock is in. So I'm going to project onto states where the observer's clock has a different energy given by S2. And so anyway, the upshot is that I haven't defined the operator phi r for you mathematically, but when you insert it into a correlation function, you can compute the correlation function with this diagram, where again, to every point here, we associate a point in space-time, and wherever you have an arrow that connects 2 points, you put in the observer's propagator, and then on the bottom and the top of the diagram, we have the wave function for the 2 observers. Yeah, so again, what's being represented here is that we act with an operator on the observer's world line, and a particle gets created and reabsorbed on the world line.
Why did you need that projector? Like, couldn't we just compute the 2-point function?
Well, yeah, if you want, you could integrate over all the different masses of the observer.
Okay.
Okay. Yeah, but it's convenient to have the projector because eventually we want to work in the time domain where we have to integrate, like, roughly speaking, like e to the I mass time over the mass, so that we can work in states where the observer, where the observer's clock actually reads like a definite time. Yeah.
So, probably misunderstood. Did you say that the propagator next to labeled by S is an observer's propagator? That's a matter propagator.
This is a matter propagator. So the propagators that are like vertical are the observer's propagator.
Okay.
And this is a matter propagator.
Yeah.
Anyway, so we just take these propagators and just integrate these functions over all of space-time, and then we use this renormalization, which I didn't have time to explain, and then we get a finite answer. And so, okay, so I define an operator called phi r. I can also define an operator called phi l, which just represents, the same local scalar field operator, just the left observer's world line. And again, I can act with phi l first and then phi r. And so here the particle that's created on the left observer's world line and propagates to the right. Or I can act with phi r first. And so these different diagrams just explain what's going on.
Here, in diagrams like this, do you have to sum multiple propagators in between the world line of the left observer and the world line of the right observer?
No, you just take this propagator as a function of these 2 points. You multiply it with the wave functions of the initial and final states, which are also functions of these 2 points. You integrate both points over all of space-time. That's the rule.
Free theory.
Free theory.
No, but even in free theory, like I'm just thinking that it's supposed that the particle S was heavy, so let's say it traveled along the geodesic. There's 2 geodesics on which it can travel, right? Around in the Euclidean picture of a sphere,
okay.
It could travel on one side or on the other.
That's true, but at the end of the day, there's just one propagator, which is supposed to represent
it's supposed to sum the 2.
Yeah, so that
the 2
propagator
paths,
did that.
But
I'm not working in
Okay.
any semi-classical limit. This propagator takes that into account.
Okay.
It's just the exact answer for the 2-point function in free theory. Anyway, so we can keep going and make the diagrams more complicated. So here I just represent a 4-point function, and of course, when we have 4 operators in the scalar field theory, we're instructed to sum over all 3 wave contractions. So the diagram looks like this. Okay, good. So I told you how the operator phi r behaves when inserted inside correlation functions. Now I'll give you the mathematical definition, which hopefully will be a little bit clearer. So the operator phi r will only act on the HQFT factor and the right observers factor. And so I'm going to write it, I'm going to take the matrix element of phi r in one of the basis states of H observer r, and then that matrix element will be valued in the space of operators that acts on HQFT. So that's how I'll define it, and basically all we do is we take this curly phi, which is the scalar field operator, and we just integrate it against these mode functions in the way that's shown here. And roughly speaking, you could think of this morally as a Fourier transform from like the space-time position basis, which strictly speaking isn't really well defined, like in the world line theory, to a momentum basis that is better defined. Because I mentioned that the quantum numbers S and N are good quantum numbers, so I sort of want to do a Fourier transform on this scalar field into a basis of good quantum numbers. And that basically is how we define this addressed global operator, sort of evaluated at the world line of the observer. And so, of course, we can also consider other local scalar field operators and address them to the observer as well, and just replace curly phi with the normal ordered product of, you know, n phi fields. It's the same thing. Sorry.
Is there a label that phi r should have in the left-hand side of the first expression, let's say? Like a moment in time or something? Or
No.
So,
Yeah, there are no labels on the right-hand side other than the dummy labels.
right, so that's
all
also,
here on the
so
left-hand
phi
side.
r should be interpreted as not an operator that acts at a point in the order lines.
Yeah, well, okay, good. So, yeah, the reason why you can't quite use the intuition that phi r is acting at the location of the right observer is because the location of the right observer isn't really a good thing to measure quantum mechanically.
Right.
So this is supposed to be our way to get around that, to define an operator using quantum numbers that are good.
But roughly speaking, the time is the canonical conjugate of SR.
Yes. So, yeah, I can assure you that when you compute the correlation functions of these operators and work in the limit where all the S variables go to infinity, where the geodesic approximation should hold, we will recover expressions for quantum field operators evaluated on the de Sitter background along the North Pole, where the observer is. Yeah. And anyway, so we can even address operators that have non-trivial indices to the observer as well. You just need to put, you know, you just need to have an index somewhere else, so we put some derivative here. Anyway, this isn't that important. The point is that we can address all different kinds of operators to the observer. Okay, so I mentioned these diagrammatic rules. There are a few simplifications of these diagrams that you can use to actually compute things. Like, for example, I can reverse the direction of an arrow, and that just picks up some factors of these S's. And likewise, I could have an arrow that comes out of the right observer's world line or out of the left observer's world line, and diagrammatically they are equivalent up to some factors, which will be important soon.
So a quick question.
Yeah.
In that first diagram, I guess in both these diagrams, what's happening is you're swapping phi r's and phi l's. If you were to write these.
Yes, exactly. It's like I'm acting with phi L first or phi R first. Yeah. Okay. Good. So now we come to how we define the Hartle-Hawking state. So we're going to define the Hartle-Hawking state to be the unique state up to normalization, such that when I act with phi L on the Hartle-Hawking state, that agrees with acting phi R on the Hartle-Hawking state. And this is something that is also true in the algebra of CLPW. And so this is the property of their Hartle-Hawking state that we chose to use in the definition of this Hartle-Hawking state in our setup. So in other words, I can take the same quantum field theory operator just to the left observer or the right observer, and it gives you the same result when acting on the Hartle-Hawking state. And so to actually estimate the Hartle-Hawking state, it's going to be a linear combination of these states where I said that we have one observer is on the North Pole, one observer is on the South Pole, but now we have a precise wave function for the mass here. It ends up being 1 over cosh pi s. And so this is true not only for the particular operators phi L and phi R, but also for any of these other addressed operators. Here, theta is the space-time CPT operator.
Sorry, this follows from the rule that you showed previously where you were allowed to move the leg of the diagram from the left to the right.
Exactly. Yeah, and we can also check this for the other dressed operators too. So, so one way that if we were dealing with like a finite dimensional quantum system, then this would be a signature that the state Hartle-Hawking is an infinite temperature state, because you can act with the same operator on the left or the right, and you get the same result. It wouldn't be true if the Hartle-Hawking state was like a finite temperature thermal field double state. Good, so that's how we define the Hartle-Hawking state, and once we've done that, the natural thing to compute is, the natural thing to measure is the mass of the observer in this state. And so this is the result over here, and so what we get, I guess in terms of the S variable, is a probability distribution for the observer's mass in the Hartle-Hawking state. And so we can check what this is semi-classically. It becomes, so semi-classically the variables S and M are the same. Semi-classically I mean that the mass is very large. And so this becomes a probability distribution over here. And you can also interpret this from a Euclidean path-integral calculation. So imagine having an observer at the north and the south pole, and the state should be prepared by some Euclidean path integral. So this is the hemisphere, the Euclidean hemisphere that would produce the Hartle-Hawking state in DS2. But now there's an observer at the north and south pole, and their trajectories can be connected by a Euclidean geodesic in the Euclidean space. And if we wanted to compute the norm of the Hartle-Hawking state, we expect that it would be computed by like the path integral for a particle that moves along this Euclidean geodesic saddle. And so, of course, the on-shell action for this thing is going to be 2 pi m, so that explains the e to the minus 2 pi m factor. But you can also do the one-loop approximation to this semi-classical calculation of a particle moving around once, and you get this one-loop factor of m, which agrees with here. So that's encouraging. Good. So let's see. How much time do I have left?
Technically 10 minutes, but you can go a little longer.
Okay. I'll try not to go too much longer. Thanks. Okay, I'll skip a few things to get to the punchline sooner. But the definition of the right observer's algebra in our story is going to be the algebra that's generated by the right observer's Hamiltonian, the operator phi r, as well as all other local operators that can be addressed to the right observer. And we're going to take this algebra to be a von Neumann algebra, so we're going to enlarge the algebra by taking the double commutant. And the left observer's algebra is defined analogously. So one thing that we find is that phi L and phi R actually do not commute with each other. They do commute when acting on the vacuum sector, but in general they don't. This can be shown by using these diagrammatic rules of like changing the direction of arrows and such. So these two operators don't commute. And something we also find is that the Hartle-Hawking state is not a trace on the algebra. So at the level of the 2-point function, the Hartle-Hawking state appears to be a trace. So to see this, you really have to look at the 4-point function. So here's the 4-point function that I showed you earlier. So here, it depends on S1, S2, S3, and S4, and if this Hartle-Hawking state is going to be a trace, then this function should be invariant under cyclic permutations of S1, S2, S3, and S4. And so for these first two diagrams it is, but for this last diagram it's not. So in particular for these crossed Wick contractions, it's these crossed Wick contractions that spoil the tracial nature of the Hartle-Hawking state. But if we take a semi-classical limit where all of these S variables are large, the observers have large mass, but the differences between different S variables is held fixed, then one can explicitly see that you do get a cyclic function of the S variables and the Hartle-Hawking state is tracial, and this is then the trace on the semi-classical algebra of CLP and W. Okay. Basically, there are no obvious candidates for operators in the commutant of AR except for the left observer's Hamiltonian. And so our conjecture is that the commutant of AR is generated by functions of AL. In a special to my model, we can prove this, but for the sake of time, I'm going to just skip the sketch of that proof. But really the upshot is that because the observer can effectively be delocalized over the whole universe, the commutant is almost trivial. In particular, what this means is that since the commutant is almost trivial, that means that well, remember that an algebra is equal to its double commutant. So that means that the algebra AR is equal to the commutant of the algebra generated by the identity and the left observer's Hamiltonian. And from this, one can see that the algebra AR is a direct integral of type 1 factors, where each each type 1 factor refers to a subspace of the Hilbert space, where the left observer's energy is fixed, where SL is fixed. Okay, so one of the key points here is that when we consider this fully dynamical and fully quantized observer, they're not described by a type 2 algebra anymore in particular, and also their commutant is almost trivial. So there doesn't seem to be a nice algebraic notion of a cosmological horizon. This is to be contrasted with, for example, JT gravity, where semi-classically there's a type 2 algebra, and even when you exactly quantize the metric and include quantum effects, you have a type 2 algebra. So one of the motivations of this work was to search for, or was just to see what would happen to the type 2 algebra when the system is more quantum. And here there doesn't seem to be some algebraic notion of the observer's cosmological horizon. Okay, I'm going to make a few quick comments on the out-of-time order correlator now of operators along the observer's world line. So this slide is just to review some basic facts about OTOCs. So if V and W are simple information operators in a large and chaotic quantum system, this is what we mean by the OTOC at inverse temperature data. I've evolved operators at different points on the Euclidean circle just so that this function can be real. And generically it looks like this. It decays in order to scrambling time. And so, so it usually takes this form, and we're most interested in the correction, like the leading exponential correction to the part where this function is flat, so like this region around here. And there's a general theorem which says that the Lyapunov exponent that tells you, how fast chaos is spreading can't exceed 2 pi over beta. And the scrambling time is logarithmic in n, where n is the number of qubits. Okay, so here's the OTOC that we're going to compute in this setup. So here's my operator phi r again, but now I'm going to consider 2 flavors of the scalar field labeled by A and B, so that there's only one Wick contraction to consider. So here pi of lambda just refers to an operator that projects onto states where the observers have a very large mass above lambda. And so when I insert pi lambda, this basically puts us in the semi-classical approximation where the observers are moving along geodesics. So now here, so tau is going to be a very large number, and so we're going to insert an operator phi a of r at a very early time along the observer's world line, and the next operator gets inserted at a late time, and then an early time and a late time again, and u1 and u2 are just order 1 numbers that are just helpful to regulate some aspects of the problem. Okay, so any questions about the setup here?
Don't you pi?
On the left?
Yeah.
That's not necessary because I only have to insert this projection once, because once we're in the regime where the observers have parametrically large mass, acting on it with these scalar field operators isn't going to take you out of the regime where their mass is parametrically large.
So that's enough. You'll see in a
Yeah.
already. one,
Sorry.
meaning only one.
Yeah, so, yeah, we're gonna take like a strict limit where lambda goes to infinity,
Okay.
and the time tau is also gonna scale appropriately. Yeah. Yeah, so we're gonna take lambda large, and we're gonna take tau to be large, and we're gonna pull fixed e to the tau over 2 lambda. So capital T is the time, where the origin of time, capital T equals 0 is the square like time.
So, but there's no notion of beta in this OTOP, right?
Good. Yeah, so I didn't put any notion of beta in. I did put a notion of lambda in, but I did not put a notion of beta in. That's correct. So, yeah, so you're probably wondering what's the thing that's supposed to give us the notion of the upper bound for
Yeah.
the chaos expert. Yeah, so we don't, that's not put in. We'll just see what the result is though. Yeah.
So what are U1 and U2?
Oh, U and U2 are just order 1 numbers that will be helpful to regulate certain intermediate expressions in the derivation. They're not important. You can set them to 0 for now if you want. Not to really important.
Real quick, just
Oh yeah.
before we get to the answer, do the 2-point functions like satisfy a KMS condition or something like this? Is there a beta I could have found?
Yeah, the 2-point functions in the quantum field theory obey the KMS condition associated with the de Sitter temperature. Yeah. Okay, good. So at very early times, the OTOC just looks like a correlation function in the QFT. So this expression over here, so omega represents the vacuum in the QFT, and then I have 4 scalar field operators in the QFT that are evaluated along the north pole geodesic at the times shown. So this is just a QFT quantity where we ignore any interesting effects of the observer. So that's what the OTOC looks like at early times, and then at very late times, the OTOC decays to 0. Okay, so I'm gonna try to go through this quickly so that hopefully I don't take too much more time. But here's the main point. So if we ignored any interesting effects of the observer, then let me take the observer's world line. Sorry, let me take the north pole to be this line over here. And if we ignore interesting recoil effects of the observer, then of course the first operator would be inserted here, the second operator up there, the third operator down here, and the fourth operator up here. But the point is, we're going to instead make the observer dynamical. The trajectory could be dynamical. And so by that I mean the following. We're going to perform the observer's world line path integral in the geodesic approximation, so classically, except 2 modes in that observer's path integral are going to be taken off shell, and they are labeled by x plus and x minus. So the idea is that when an operator acts on the observer's world line at point 1, the observer could be deflected in their new position at future infinity, because we're evolving from long times, will be point 2, which is parameterized by x plus, which is a coordinate along future infinity. And then after acting with operator 2 and evolving backwards in time, the place where the observer ends up on past infinity will be called point 3, labeled by x minus. And then when we evolve future in time again, the observer will be at point 4 because we're projecting the Bra state is a Hartle-Hawking state, so we're projecting onto the observer being at the north pole.
Sorry.
Yeah.
I might have misunderstood this, but I thought that you said that acting with these operators don't really away from the infinite lambda limit. So basically for an infinite mass limit for the observer, but would an infinite mass observer always stay on the...
Yeah, so we're taking the limit where the observer has infinite mass, but we're also, tau is parametrically large.
Yeah, but then...
Yeah, so in other words, a small perturbation in the far past is going to be amplified and non-negligible at future infinity.
Yeah, I guess my only question is, in the previous slide you said that projector over lambda, you don't need it on the left-hand side because any actions of those phi at any time does not bring you away from the infinite mass of the observer limit, but this seems like it's doing that.
Well, the mass is, okay, so we're just saying that the mass has to be above a cutoff lambda, and lambda is parametrically large. And when you act with the scalar field just the observer, that's only to change the observer's energy by like an order 1 amount. Yes. Well, yeah, but also just in general, the observer's energy will only change by an order 1 amount. But now we start in an initial state where the observer has parametrically large energy, so we'll always be in the regime where the observer's energy is parametrically large. Yeah. Okay. Okay, so maybe in the interest of time, I'm not going to go over the details of this OTOC explicitly, but the point is, we're just taking a 4-point function in the QFT, where the 4 operators are measured as red dots, and then integrate over x plus and x minus, where s is the action, given it's the world line action of this blue trajectory. Okay, so I'm going to skip these steps, but the point is, mathematically, you could rewrite this as something that looks like a scattering amplitude of, okay, cool. Oh, this isn't good. I'll just finish my sentence. You can rewrite this you can rewrite this OTOC as something that looks like a scattering amplitude of 2 very boosted shock waves near the observer's horizon. Okay, I'm not going to review each line here, but the point is, I kind of exchanged the x plus and x minus for a p plus and p minus, just doing the Fourier transform. So x plus was a coordinate along future infinity, and further away from future infinity, that actually corresponds to a translation of Poincare time, which looks like a translation along the observer's horizon. So that's why p plus and p minus enter here. Okay, so you can, if you're interested in more details, I'm happy to discuss afterwards, but the key takeaway point is that you can rewrite this OTOC as an iconal scattering amplitude, and the way that it differs from calculations in ADS is that the iconal phase can have either sign, whereas in ADS, the iconal phase can only have a particular sign, which refers to the fact that in ADS, the effect is due to gravitational time delay, and there is no gravitational time advance. So here, you can sort of effectively have gravitational time advance, though I emphasize that this is a different effect that's producing this OTOC, and I've just done the mathematical rewriting of this observer's path middle to look like an iconal scattering amplitude. Okay. Good. So maybe one thing I should mention is why the Lyapunov exponent is 4 pi over beta ds. Basically, the leading thing gets directed in powers of e to the tau over 2 pi, and basically, well, if you think of it in this iconal language, okay, I guess, what's the most fastest way to say this? Roughly speaking, you can imagine that the leading correction to this OTOC is given by looking at how a 2-point function changes when you apply one of these isometries described by the red arrows to one of the points. And the point is that in de Sitter space, this isometry is acting transverse to the observer's world line, and so the leading correction to a 2-point function would be second order in a small parameter, whereas in ADS, the isometry that kind of acts along the horizon acts longitudinally along the observer's world line. Okay, in the interest of time, I can discuss that more with people afterwards. But let me just get to the interpretation of this. So, yeah, so one puzzling thing is that the Lyapunov exponent is greater than 2 pi over beta de Sitter, which is the naive upper bound if you assumed that the chaos bound should hold. So maybe this means that the OTOC in dual description should be computed at some temperature that's larger than the de Sitter temperature. Maybe it should be computed at infinity. So anyway, that's a question that was already raised. What's the temperature here? Okay. Well, okay. I can say what I have to say. That's just in words. Okay. Okay, so one point I did want to make though is that because the scrambling time is logarithmic to the observer's mass, one interpretation of that is that in the putative dual, the Hilbert space that's used to describe the scrambling physics has a dimension that grows with the observer's mass. On the other hand, when you consider an observer in the static patch, as the observer's mass increases, the entropy of the static patch decreases. So you would imagine that actually the space, the dimension of the Hilbert space in which an observer has a given mass should decrease as the observer's mass increases. So these two considerations seem to be in tension with each other. And maybe we could discuss that more, but I consider this to be a puzzle. Okay, so now this is just the summary. So we quantize the system of two observers in a scalar QFT in two-dimensional de Sitter. We defined the bright observer's algebra and argued that its commutant is almost trivial. And furthermore, we argue that the observer's cosmological horizon emerges when the observer has a large mass and is moving along some geodesic. But away from the large mass limit, we were not able to find an algebraic analog of the observer's horizon. Furthermore, the OTOC naively indicates that chaos spreads faster than the maximum rate that's allowed for large and chaotic systems, so this is difficult to interpret as well. And something like this would be a target for any putative holographic dual. And then just for some future work, it would be interesting to consider the case where G unit is finite, and maybe in three-dimensional de Sitter gravity we can quantize the metric, at least starting conservatively, and see where that would lead us. And also, we've assumed that our clock has infinite entropy because we took the mass to be a continuous parameter, but that's not realistic. So, having a finite entropy clock would also affect the results of measurements. So, anyway, there are multiple ways that we can generalize this setup to be more realistic, and that can be explored further. Okay, so thanks for your time, and I'll leave it there. Thank you.
Questions for David?
Yeah, maybe this is a little bit stupid, and you probably said this like a lot of times, but I still didn't 100% get why say here if you consider 4-point function, you have an algebra like basically type 1 integral, type 1 factor, while previously in CLPW that you said they're considering 2-point functions, and then they're getting type 2.
Yeah, so why did they get type 2 and why did I get type 1?
Yeah, maybe more physically, because I would have thought that in their case, how they got from, say, the QFT on curve background type 3 algebra to type 2 is to include perturbative gravity effects.
Mm-hmm.
And here it seems that you're also dealing with not the non-perturbative level, still at the perturbative level, and we're considering a little bit more of the complicated observables. But then this changes the type of algebra. This makes me a little bit unclear why.
Yeah, so roughly the idea is that when the observer is dynamical, okay, so when I say the observer is dynamical, I mean that their trajectory is not going to be confined to the North Pole. When you act with operators, they can take a different trajectory, and you can even act with operators and evolve forward and backward in time many different times, so that the observer can move on some, arbitrary trajectory almost. It can explore basically the entire space-time. So what this means is that the commutant of the observer's algebra is going to be trivial or almost trivial. The observer isn't confined to a horizon. So if the observer's algebra, if the commutant of the observer's algebra is trivial, so if the commutant of the observer's algebra was actually trivial, was the identity, then the double commutant would be the algebra of all operators on the Hilbert space, which is type 1. So in our case, it's almost like this. The commutant of the observer's algebra is going to be generated by the other observer's Hamiltonian, which is almost trivial. And so the double commutant of that is going to be the algebra of all operators that do not change the left observer's energy, which is a direct integral of type 1 factors, where each factor refers to all the operators that act on the Hilbert space where the left observer has a fixed energy. So it's just, it just has to do with the fact that when the observer can explore the entire space-time, it's like the same reason why the algebra in QFT for an entire space-time is type 1. The observer basically is exploring the whole space-time.
Would you say for a two-sided black hole that if you had an observer of finite mass, the algebra of that describes that observer is actually type 1?
Then the algebra is type 1.
Because they
Sorry, in what band?
Which
a
is
two-sided black hole.
Where's the observer?
Let's say it doesn't really matter. It starts at the right side, but in principle, when you act with operators, it also recoils.
Yeah, and you can
It's
evolve.
not the same, right? Semi-classical you have interior. Here you don't have any, you can see.
Yeah, but I thought the important thing is that through these recoils that you consider at finite mass, when the observer has finite mass,
Yeah,
the observer no longer travels on a geodesic.
right.
And in a two-sided black hole, if the observer doesn't travel in the geodesic, and you
Even if it
allow-
does travel on a geodesic, it would fall in.
it would fall in, but it would never explore.
No, but there are times like two
Sure.
of it would hit the ball with both boundaries, presumably, no? Oh, no, sorry.
Need not, it can be
no,
a
it need-
normal one.
It need not, but it could.
It need not, but it could. Yeah.
Yeah, and you can evolve forward and backwards in time as well. So I don't see an obstruction to, the causal diamond being able to explore the whole space. Yeah, I would say that it would also be type 1 in that case.
Wait, then it means that if you have a two-sided black hole, you have two CFTs, right? And you can see this type 1 thing from CFT calculation. I mean, cognitively.
Okay, let me be clear. Yeah, people have used the word saying that if you can, if you can find the effects that convert the type 2 algebra into the type 1 algebra, then you've solved quantum gravity. That's certainly not the case here. So this is a more trivial type 1 statement.
Yeah, I'm just a little bit confused of how you can see the type 1, say, from the CFT, but without including non-perturbative corrections.
Sorry, but currently the idea is that you would have some holographic theory living on the holographic screen given by the Worland of the observer, so you don't just have the two CFTs at that point, right?
I think your algebra is type 1 the same way that the entire bulk
Yes,
of the algebra is type 1.
yes.
The union
Yes.
of the two CFTs is a type
Not
1.
a CFT.
Yeah, right. The algebra acting on both CFTs is a type 1. Yeah. Okay.
I have
Yeah.
two questions. One, if I take, with your wave function psi Sn, if I take S large and then do the sum over n that you were doing to define the vacuum, I'm just localizing, is that the interpretation of basically like e to the I n theta integrating, summing over it to create a delta function at theta equals 0 or something?
You're considering
I want to understand the sense in which your particle is delocalized at small s, but at large s it localizes.
do you mean this do you mean
No,
this?
earlier. So when you were defining the vacuum there.
Oh yeah, this thing.
Yeah,
Okay.
so the Sn, should I think of the sum over n as basically, am I allowed to say for a given value of S, suppose S is large, psi n is basically the wave function of the particle.
Yeah.
And
Yeah.
so for large S, when I do the sum over n, it presumably just gets me two delta functions localized on the pole and antipode.
Yeah, that's basically the idea. So actually, this function over here is the antipodal degrees function. So it's the thing that diverges when the 2 points are at antipodes.
Okay,
That's where basically it has its support.
but
Yeah.
but it's true also at small s, at all s.
Well, at any s, it is an antipodal degrees function.
I see. So, is there some sort of an easy picture here for understanding why for small s the location of the particle is? I just want to have a sense of, if I were to describe where your observer is at a given s. So I should still think that you're starting out the particle exactly localized, and only when you act with other fields it spreads around.
Okay, so if we're working in this fully quantum treatment where f is finite, then strictly speaking, the operator that tells you where the particle is not a good operator. Like this, yeah.
Yeah, but is there not a wave function associated to the?
Well, yeah, I mean, yeah, there's still, yeah, you still have a wave function.
And they seem completely localized here,
Well,
right?
well, this wave function is not a delta function that sets the 2 points to be the same. Yeah, it is, but well, first of all, this wave function isn't normalized in any special way either. So this wave function is a function that diverges when the 2 points are antipodes.
Okay.
So there's a sense in which its support is concentrated
I see.
where the 2 points are antipodes.
I see, but it's not two specific points, any 2 points. I see.
When these L and R points.
Right.
Yeah.
And the second question is a little bit, so you say your result lowers the credence of whatever quantitative holographic, like it lowers the credence of the S decider playing an important role in that theory, right? In your
Yeah. In a sense, it does. It lowers the credence that. In other words, there seems to be tension between assuming this conjecture that the holographic student is the observer's world line. There's tension between having a theory that reproduces correlation functions on the observer's world line and having a theory that gives a microstate count of the de Sitter entropy. So, yeah, those two things seem to be in tension with each other, unless I've interpreted this wrong. But yeah.
I have a question about whether, if you did this in a de Sitter, so one reason is your interpretation de Sitter is that the purely holographic dual would be on the world line.
Yeah.
So if you did this in the ADS setup, would you expect that that's telling you essentially that whenever you have this observer, you would not, the two CFTs, say in a double-sided black hole, would not describe the whole thing?
Well, yeah. Well, that's related to this paper you had recently, right?
Yeah, I wanted to know
Yeah.
whether from this angle you have a similar intuition or.
Well, did anyone do the OTOC calculation for an observer and ADS?
Well, one comment is that, so the main, well, no, but if you did do it, one comment is that, so in de Sitter space, the scrambling, the chaos came from expansion, so you're not going to have that in ADS. Like if you have a small perturbation, it's going to come back to the original world line. So in that sense, it wouldn't appear to be chaotic. Now, people have considered observers in ADS CFT in many contexts. I guess maybe there was some work by like Jafferis and collaborators where they wanted to ask, what is the CFT dual of the observer's Hamiltonian? So that's an interesting question to ask, and I think their approach was to entangle an observer with some like auxiliary system and trace that out, consider the modular Hamiltonian of this entangled state. And that's supposed to think, and then they wanted to use that to evolve operators localized near the observer along the observer's world line. Yeah, so there is some proposal for how to think about observers in ADS CFT. So it would be interesting to, pursue that further, or, ultimately, yeah, so the test of that would be to compare those correlators with ones who compute ADS CFT also. Yeah, so people have thought about that, yeah.
But that proposal, I think, actually ends up telling you that whatever happens along the border of the observer can be observed from the dual CFT.
Yes.
So,
Yes,
in
this
fact, this sounds like
Yeah.
you would not have a screen along the world line.
Yes.
So if it's not true in ADS CFT, why should it be true in DS?
Well, you don't need it to be true in ADS CFT. In this case, the observer would be the ADS boundary. You're allowed to call the ADS boundary an observer. So in DS CFT, we don't have that, and so we have to work with something, and we just have this conjecture that there was some evidence for the semi-classical limit from CLPW, and now we're just pushing that further away from a limit that they consider. And yeah, there are multiple puzzles. Yeah.
Any other questions?
Now let's activate it again.